In this video, I'm going to give you some quick notes for sections 7.1 through 7.3. In this chapter, we're going to take kind of a different turn here with these trig functions and not look so much at finding trig values, but looking at the relationships between some algebraic combinations of how the trig functions react with one another and what they do when we combine them. These form identities, which are equations that are always true. So in 7.1, we focus on a few of these identities, and mainly they are the Pythagorean identities and the sum and difference identities. So all this week, you're going to be working on identities, which are just equations that contain trig functions. Sometimes you're just going to be simplifying using them, and sometimes you're going to be using them to calculate things. Next week, you are going to be taking a quiz with these identities because you need to get really familiar with some of the basic ones. Some of them are more complex and aren't used very often. I'll tell you which ones you need to know and which ones you can kind of forget about. I also am going to post on our Moodle page a document that has all the identities just on one page for you to reference. So right at the beginning of section 7.1, there are some basic identities. And these identities you should have learned back in chapter 6. They have our reciprocal identities and our quotient identities. So you should have already learned that sine of x is 1 over cosecant x. And cosecant x is 1 over sine x. That is a reciprocal identity. Reciprocal in algebra class, reciprocal means flip. So if you flip sine, you get cosecant. If you flip cosecant, you get sine. And the same is true for cosine and secant. And the same is true for tangent and cotangent. So you've probably already worked with these, but we didn't really call them identities before. We just called them reciprocal functions. But these are our first examples of identities. These are equations that contain trig functions, and these equations are always true. So these are examples of identities. The quotient identities are how we can use sine and cosine to create tangent and cotangent. So tangent is sine over cosine, and you probably used that one when you found tangent values on the unit circle. And cotangent, well, since cotangent is the flip of tangent, cotangent is going to be cosine over sine. And those are considered quotient identities because we're creating tangent out of a fraction of two other trig functions, and quotient means fraction. So these are just some basic identities that most likely you are already familiar with. There are a few other basic identities listed right at the beginning of 7.1, and they are some negative, negative angle identities. And I'm going to show you why these are true with an example on the unit circle. So these negative angle identities say that sine of negative x is going to always be the same thing as negative sine of x. And cosine of negative x is always going to be equal to just cosine x. And tan of negative x is always going to equal negative tan of x. So notice that in sine and tangent, the negative comes out, but in cosine it does not. It just disappears. And if you look at the pattern of the signs on your unit circle, and I'm just going to use quadrant 1 and quadrant 4 as an example. In quadrant 1, everything is positive. And in quadrant 4, cosine is positive. And then sine and tangent are negative. And then anything that has the same reference angle is going to have the same trig value. You just might have to change the sign based on the quadrant it's in. So if I were to ask you what the sine of negative 30 degrees was, negative 30 degrees just means you're going clockwise 30 degrees instead of counterclockwise. So negative 30 degrees, well, that puts me in quadrant 4. That means my answer is going to be negative. My answer is going to be negative. And that angle has got a reference angle of 30 degrees. So it's going to have the same trig value as sine of 30 degrees. I just have to make my answer negative. So sine of negative 30 degrees is the same as negative sine of 30 degrees. Now if I do cosine of negative 45 degrees, that means I'm going clockwise 45 degrees. So down in quadrant 4, cosine is positive. And that reference angle is 45 degrees. So this answer is going to be positive because in quadrant 4 cosine is positive and the reference angle is 45, so it's going to have the same answer as whatever cosine 45 is. So notice the negative sign just disappeared. With sine, you can pretty much think of it as the negative coming out front, but with cosine it disappeared. And then with tangent, if we do, let's say 60, just so we can see a different value, if we do tan of negative 60, that's clockwise 60, which takes us into quadrant 4. In quadrant 4, tan is negative, and it's a reference angle of 60. So as long as we use the correct sign, which is negative, we can just do tan of the reference angle. So negative tan of 60. So that's just an example of how these work. And the same thing would be true between quadrant 2 and quadrant 3. We would just be working with larger angles. We would be working with angles between 90 and 270 is all, and negative 90 and negative 270. So with sine and tangent, the negative pretty much comes out front. With cosine, it just pretty much cancels. So those are our negative angle identities. Probably the most important trig identities, and they get used most often, are the Pythagorean identities. There are 3 of them, But if you remember just the first most basic one, you can come up with the other two. So you don't necessarily need to think of it as memorizing three separate identities. Our unit circle, the reason it's called a unit circle is because it has a radius of 1 unit. So if you remember back from algebra class, this is a circle centered at the origin with a radius of 1. The equation for that circle would be x squared plus y squared equals 1. And if you remember, the points on the edge of this circle were cosine theta, sine theta. The x values were cosine and the y values were sine. So if we replace the x with cosine and we replace the y with sine, in that equation for the circle, we get cosine squared theta plus sine squared theta equals 1. That is one of the Pythagorean identities, and it's just based on the formula for a circle with radius 1 centered at the origin, and we're replacing the x and y coordinates with sine and cosine because that's what the x and y values are on our unit circle, sine and cosine. Now, we can rewrite this formula lots of different ways, and we just rewrite it with algebra. So you're not always going to use it in this format. You'll very often see the sine and the cosine switched. Makes no difference what order you add in. It's still the same formula. Sometimes you'll use this to replace sine squared or cosine squared in the problem. So we can take one of those and subtract it over to the other side. So we might say cosine squared equals 1 minus sine squared, or sine squared equals 1 minus cosine squared. And if we reverse the order of the subtraction, that's going to negate these values. So negative cosine squared equals sine squared minus 1, or negative sine squared equals cosine squared minus 1. So there are lots of different ways that we can rearrange the terms in that formula, but typically this is the one that you see most often described as being the Pythagorean identity. But in practicality, when we use it, we may have to move the terms around so that we could use it in lots of different ways. So if we know this one, if we know just that one, there are two other Pythagorean identities that use our other trig functions, and we can create those other two trig identities just from that one. And we just have to do some creative addition and subtraction, or excuse me, multiplication, or division, sorry, some division. So what I'm going to do for Pythagorean identity number 2, we're going to call this number 1. This is, this is our most basic. For number 2, that is not a 2. I am going to take my basic one and I'm going to divide everything by cosine squared. I'm just going to go through that equation and divide everything by cosine squared. So I've got sine squared theta plus cosine squared theta equals 1. I'm going to divide everything here by cosine squared, and then I'm going to simplify it. using algebra and trig identities that we already know, the basic ones from last chapter. So we've got a trig identity for sine over cosine. It's one of our quotient identities. Sine over cosine is equal to tangent. So that is tan squared theta. Cosine over cosine, we can simplify that with algebra. Anytime the numerator and denominator match, it's equal to 1. And then 1 over cosine, that's a reciprocal function. We could rewrite that without a fraction as secant. That is Pythagorean identity number 2. And again, if we need to, we can rewrite those terms in all different ways. Right now it's tan squared plus 1 equals secant squared. We can change the order of the addition. We could subtract either one of those terms over to the other side. So I could say 1 equals secant squared theta minus tan squared theta, or tan squared theta equals secant squared theta minus 1. Also, I could change the order of the subtraction, which will change those sides to negatives. So negative 1 equals tan squared minus secant squared, and negative tan squared equals 1 minus secant squared. So this is the most basic that we usually will see, but these are variations that we might see and we might have to create based on the needs of the different problems. And this is how we can just use the original Pythagorean theorem to create it and not necessarily think of this as a second equation that we need to memorize. If we really can just memorize that first one and then divide through by cosine squared to create this one and not have to memorize this. So we're going to do pretty much the same thing to come up with the third one. So for Pythagorean identity number 3, we're going to divide everything by sine squared. So we're going to go back to the original Pythagorean theorem, and I'm going to go through and divide everything by sine squared and use either algebra or trigonometry to simplify all 3 of these terms. And that will give me my third and final Pythagorean identity. So sine squared over sine squared, that's just algebra, top and bottom match. I get 1. Cosine over sine, that's a quotient identity. Cosine over sine is equal to cotan. And then 1 over sine, that's a reciprocal identity. We could write that simpler as cosecant. So 1 plus cotangent squared theta equals cosecant squared theta. This is Pythagorean identity number 3. And you don't need to memorize it. You can create it from the original just by dividing through by sine squared. And again, even though this is the most basic format we see it in, we can rearrange the terms based on how we need to use this in a problem. We might need to change the order of the addition and still be able to recognize it. We might need to subtract either one of those terms over to the other side. So cotan squared theta equals cosecant squared theta minus 1, or 1 equals cosecant squared theta minus cotan squared theta. And then we might need to change the order of that subtraction. And when you change the order of the subtraction, it changes the sign of the answer. So negative cotan squared theta would be 1 minus cosecant squared theta, and negative 1 equals cotan squared theta minus cosecant squared theta. So those are just all kind of algebraic variations. This one is the most basic, and we got it just by going back to the original and dividing through by sine squared. So there is a Pythagorean identity that involves each of our 6 trig functions. The most basic involves sine and cosine. If we divide through by cosine squared, we get one that involves tangent and secant. And then if we divide through by sine squared, we get one that involves cotangent, cosecant. So those are our Pythagorean identities. And these are really important. These come back over and over again in other classes. And if you're going to take any calculus courses, you will see these again. So I'm going to go over the sum and difference identities. This is probably going to end up being just a video on 7.1, so I don't end up making it too long. I don't want you to sit here for an hour watching a single video. So I'm just going to do my sum and difference identities and maybe a couple of quick examples and do a separate video on 7.2. So the other important identities in 7.1 are the sum and difference identities. And the sum and difference identities are how to deal with a trig function that tells you to add or subtract angles. And they group these together because if you remember back in algebra class, subtraction is really just adding the opposite. So the difference formulas look exactly the same as the sum formulas. It just changes the signs. The formulas themselves can sometimes look a little intimidating. There's a lot of information here. When I actually go over an example, hopefully it'll clear it up though. So if you are asked to either add or subtract inside of the angle of a trig function, you cannot simply do the trig value for each of them. That would be like distributing the trig value. You can only distribute for linear functions. So think about this. If there was a square outside the parentheses, you would not be allowed to distribute. If there was a square root around it, you would not be allowed to distribute. If there was a natural log in front, you would not be allowed to distribute. Trig functions are the exact same way. You are not allowed to distribute the sine function and do the sine of each of those angles individually. You would not get the answer that they're looking for. So there is a formula for how we would evaluate the sine of the sum or difference of two angles. So I've got a little story that goes along with this, and it usually helps some people. There is a pattern for sine and cosine, and this is going to sound really crazy and really weird, but it has always helped me to remember the difference between the two. And for some reason, I always think of math as people. Math formulas and math functions and variables as people. So sine is the nice guy, and cosine is the mean guy. So sine likes to share, and cosine does not. So sine is our nice guy, and cosine is our mean guy. So what makes sine the nice guy is that he's going to take on the first angle, and then he's going to share. He's going to let cosine take on the second value. So he's sharing. Another thing that's nice about sine is that if there's addition inside this angle, he's going to keep it. He's not going to change it on you. He's going to go ahead and keep it. Or if there's subtraction inside that angle, he's going to keep it. He's not going to change it on you. If there's subtraction in there, there's subtraction in the formula. And then he's going to continue his sharing and say, okay, I got a turn with you, you got a turn with V, let's switch now. So now I get a turn with V, and you get a turn with U. So he intermingles with the cosine, and he shares. And he keeps the same sign. So if the angle has addition, the formula is going to have addition. If the angle has subtraction, the formula has subtraction. So really, this is two formulas in one. If your formula uses the operation on top, use the one on top over here. If your angle uses the one on bottom, use the one on bottom over here. So cosine is the mean guy. He does not like to mingle, he does not like to share, and he's going to change the operation. So for cosine of u plus or minus v, he does not like to mingle, and he does not like to share. He's the bad guy. So he's going to take both of them. Cosine u, cosine v. He's mean, bad. He's going to change the operation on you. So if there was addition in the angle, he's going to change it to subtraction. If there was subtraction in the angle, he's going to change it to addition. And then he'll let sine take on the u and the v. So if you're adding here, you're going to subtract here. If you're subtracting here, you're going to add here. So sine is the nice guy. He likes to mingle, he likes to share, he keeps the sign the same. Cosine's the bad guy. He doesn't mingle, he doesn't share, and he changes the sign on you. So it's not really important to memorize the tangent formula, but because tangent, remember, is sine divided by cosine, tangent of u plus or minus v is going to have some of the properties for sine in the top and some of the properties for cosine in the bottom. So there's going to be some mingling and sharing and keeping the same sign in the top, and there's going to be some changing of the sign and some greediness in the bottom. So tangent of u plus v, in the top, you're going to do tan u plus or minus tan v. Okay, so they got separated, and you kept the same sign. Just like up here, sine u and sine v are separated into two separate terms. In the bottom, it's going to look more like cosine. So it's going to be 1 minus tan u tan v. So there, they're together, kind of like here, cosines are together, and it changed the sign. Oh, minus plus, sorry, minus plus. So, for example, if we were adding, in the problem we were doing, we would add in the top and we would subtract in the bottom. If we did a problem and we were subtracting in the angle, we would subtract in the top and we would add in the bottom. And we'll do an example of this here in just a minute. The reason that we are doing these three identities is so that we can expand how many angles we can find exact values for. Right now, we can only do exact values for multiples of 0, 30, 45, and 60, or 90, those values that are on our unit circle. But if we can start adding and subtracting those angles and plug them into this formula, their values into this formula, we can now get exact values for more angles. So I'm going to go through a couple of examples really quickly, some that don't have us find values, that are just asking us to use some of our identities to simplify, and then some that are asking us to find values. And all of these examples are out of the book, but the examples in your homework should be very similar. So the first one that I'm going to do asks us to simplify tangent of x times cosine x minus cosecant x. Now, in a lot of these simplify problems, you're not only going to be working with trigonometry, but you also have to remember everything you know about algebra. So don't forget all the simple algebra stuff you could do as well. So here, I'm just going to start with multiplying. I see a set of parentheses with something in front of it. In algebra class, I would be tempted to go ahead and distribute. So that's what I'm going to start with. So this is tan x times cosine x minus tan x times cosecant x. And that almost looks worse now, but in a second it's not. Whenever you're dealing with a problem that's got a bunch of different trig functions in it, you can always change everything back to sines and cosines. Because remember, your quotient identities allow you to change tangents and cotangents back to sines and cosines, and your reciprocal functions allow you to change secants and cosecants back to sines and cosines. So what I'm going to do is I'm going to change everything now to sines and cosines. So tangent is sine over cosine. And I can leave this alone because it's already a cosine. If you want to, you can write it as a fraction if you're more comfortable with everything being fractions. Tangent, again, is sine over cosine. And cosecant is 1 over sine. And I'm going to cross off everything I possibly can. Anytime we've got something that matches in the top and the bottom where we're multiplying, we can cancel. So here I've got cosine over cosine, and here I've got sine over sine. This is going to leave me with sine over 1, which is just sine. This is going to leave me with 1 over cosine. And with trig, we don't ever want to leave a fraction if we don't have to. There is another function that's equivalent to that. So I'm really going to write this as sine minus secant. That's the most simplified form. We don't ever want to leave fractions in trig if we don't have to. If there is a different function we could write, we want to do that. So that original tan times cosine minus cosecant is equivalent to sine minus secant. Now I'm going to do another one, and this next one is going to involve Pythagorean identity. And again, it's just telling me to simplify. We want to simplify that as much as possible. Sine to the 4th x minus cosine to the 4th x. Well, without those trig functions there, the trig functions make it look a little bit more difficult than it needs to be. it's really just a factoring problem. It's a difference of squares. Even though those aren't exactly squared powers, they are even powers, which means I can split them in half and do one with plus and one with minus. So this is sine squared x minus cosine squared x, sine squared x plus cosine squared x. And now I'm going to go back up towards the top because this is an identity. Sine squared plus cosine squared. This is where we can replace something because there's an identity that says it has a different value. And I'm going to go way up here. Sine squared plus cosine squared is equal to 1, which means we can replace sine squared plus cosine squared with 1. This entire thing can be replaced with 1. And multiplying by 1 doesn't change anything. But we're still not done because this other factor is still a difference of squares. So we can factor this one more time by splitting the powers in half and doing one with a minus and one with a plus. Now this one is not a Pythagorean identity. Pythagorean identities will always have squares in them. So this is really as far as we can go. So we were able to take out that piece right there with a Pythagorean identity. And now I wanted to do one where we find an exact value using a sum and difference formula. So I'm going to find the exact value of cosine of 75 degrees. Because it says exact value, that means I need to use an identity and I need to use unit circle values. Now 75 degrees is not an angle that we have marked on our unit circle, which means we need to break 75 up into pieces that are on our unit circle. So we need to come up with a way to break apart 75 into angles that are on our unit circle. And the way that we can do that is if we write this as cosine of 45 plus 30. 45 plus 30 is equal to 75. And now remember what I said, we can't just do cosine of 45 plus cosine of 30. We can't distribute the cosine. The same way we can't distribute a square, and we can't distribute a square root, and we can't distribute a log. We have to use the formula. And now remember, cosine is our bad guy. He's the mean one. He doesn't like to mingle. He doesn't like to share. And he is going to change that operation on you. So cosine is going to take on both of those values. So we're going to do cosine of 45 and cosine of 30. And those are going to be multiplied together. And then we're going to do subtract. And then we're going to do sine of each of them. Sine of 45, sine of 30. Now all four of these values we can pull off the unit circle. And we want exact values. So we need to do them in fraction form with the radicals. So cosine of 45 is radical 2 over 2. Cosine of 30 is radical 3 over 2. Sine of 45 is radical 2 over 2. Sine of 30 is a half. Now I can multiply I get radical 6 over 4 minus radical 2 over 4. They've got common denominators, so I can go ahead and put those numerators together, but I can't combine them. Those terms are not like terms. You cannot combine radicals with addition and subtraction unless they are the same type of radical. So a root 6 and a root 2 are different types of radicals. So the exact value for cosine 75 is radical 6 minus radical 2 over 4. And if you want to, you can check it in your calculator, make sure you're in degree mode. You can type this one in as a decimal and then type cosine 75 in to your calculator and make sure they come out the same, and they will. And I'm going to do that real quick just to show you. Radical 6 minus radical 2, type that in first, and get an answer, and then say divide by 4. So in my calculator, I've got 0.25882 approximately, just because I'm out of space over there. And then when I type cosine 75 in my calculator, I get approximately 0.25882. Exact same number on my screen for both of them. So, perfect. Excellent. I know I got it right. Okay. So these sum and difference formulas allow us to find exact values for more and more angles. And I'm going to close out this video with a problem that really doesn't require any work at all. It just requires you to recognize a pattern. We just want to identify the trig value that's being calculated. If I said sine of 37 cosine of 22 plus cosine of 37 sine of 22, that is the setup for one of our identities. And we want to know which one, and we want to kind of go backwards to figure out what they're trying to calculate. So notice that our sines and cosines are mingling. Sines and cosines are mingling. So which one of our identities mingles? The sine function mingles. And does the sine function keep or change the operation? The sine function keeps the operation. And then we pull those angles out. This formula is being used to calculate the sine of 59 degrees. So you're not really being asked to calculate anything, but just kind of recognize what you're seeing here and what they're trying to do. Just a way to solidify that identity in your head a little bit. So there's certainly a lot more practice problems in 7.1, all of them a little bit different than each other, but I hope this helps a little bit. This is 45 minutes just on section 1, but that's pretty much all of it, but still, again, a lot more practice problems. But I hope that's enough to at least get you started. I will do another one here on 7.2, and I will post that separately, and I will also post these notes if anybody would like to have a copy of these notes to go along. These will all be on our Moodle page. And just email me or come by the Math Tank if you have any questions. Have a great day.